Hello everyone. In the last session we are seeing the conductors. So today we are going to continue with this. So in the last session we have seen that in the solid non-conductor we have a total energy stored is, that is 3 by 5 kq square by r square. If this is a total energy, and also we have seen that also we have seen one more thing, that is outside from, see, this is the energy from 0 to r, or you can say this is my better to say it as the energy is between 0 to r only, but this is the total energy. Okay, this is a total energy. I'm just adding in this only. This is my total energy. So if I ask you, if someone asks you, because there is a one question, I am seeing the previous year question, there is a one question they ask the energy which is present inside this sphere, means inside energy. Separately they are asking inside energy. So for inside energy, see, outside what is the energy? Outside, if I ask you, this is a total. Outside we know what is the energy, that is we have derived also, that is kq square by 2r, that is the outside energy. So just subtract this value, you will get the internal like inside energy. What is the inside energy will be there then? Inside, how much the value we will get? Inside will be, we will get how much? That is, if you subtract, how much you will get? Subtract this na, that will be kq square by 10r square. Are you getting my point? So that is the inside value and that is the outside value. That is what I am trying to clear. So just note down this. That is also an important part. Okay, I hope it is clear now. So now in today's session we are going to do some more examples on the conductor. I hope you remember all the formulas. That is very simple. We have two cases. One case we have seen, another case we have also seen. In one case, first case, the internal electric field is 0, potential is kq by capital R, that is a constant value. External electric field is kq by r square, and the external potential is kq by small r. Then after that we have to go for the non-conductor. In non-conductor case we have another case where we have seen the internal electric field is rho r by 3 epsilon naught, or you can say it is kq small r by capital R cube. Then after that we have seen the outside electric field is defined as kq by small r square. Then we have go for the potential. Outside potential is kq by small r, but the internal potential is very different, that is kq by 2 capital R cube into 3 capital R square minus small r square. Then we have seen the graphs also, and after that we went to the potential energy. We have seen for the conductor case, and on the first case we have seen the potential energy is stored in kq square by 2r square. And then we went for the non-conductor case, and we have seen that the potential energy stored is 3 by 5 kq square by r square, and we have seen inside the energy is kq square by 10 r square, and the outside the energy is kq square by 2 r square. I hope it is clear till here. Everyone is clear. So now in the next now in today's session we are going to solve the example on the conductors. Clear? You should remember the formula, then only you are able to understand the things better, in a better way. Clear? So we are in this session we are going to solve a lot of examples. Okay, so let us start. I will go slow in this session. This session will be little, I will go slow. Just you try to understand the things a better way. Okay, because this will be slightly difficult lecture, but you have to be patient because it is going to open your all the concepts. If you survive this lecture, then I am sure that you can solve any questions of conductor, any questions, like not a one, any question from any book, anything. Just be patient. Patience, not patient. Suppose I have taken all are second case. Okay, all treat all as a second case. This is the charge we have. Okay, so assume this is the charge we have, everything is there. Okay. And it is center. This is my center, obviously. This is the center, and the radius is capital R, that is given. Correct? A frictionless, everything is there. Okay, ideal condition. Example 1, first example. Okay, I taken a one electron. Okay, I have taken a one electron. The electron, or not electron, take it as minus charge for having a mass m. Okay, and I send it with a velocity of v naught, or I just send this particle, or I just keep this particle here. So where it will be moved? First you tell me where it will be moved. Obviously it will be moved in this direction because the electric field will be like this. So it will move in this direction, it will be attracted, it will move toward the center. My question is that what is the velocity at the center? Means if this is my center, right, what is the velocity at the center? That is my question. Simple question. Clear? First question is very clear. I hope it is clear. There is a charge minus qm. I'm just keeping this charge, it will move in this direction. My question is what is the velocity at the center? Just calculate it. This is a very simple question. Simple. You have to see first thing, what is the thing that is clicking in our mind. As everything is ideal condition and it is electrostatic force. Electrostatic force is a conservative force, so we can apply the work energy, like energy conservation. And if energy conservation is applicable, U initial plus K initial is equal to U final plus K final. Correct? This point, what is the potential? What is the like potential energy at this point? That will be KQ by R into minus Q. Correct? What is the initial kinetic energy? 0. What is the final? KQ at center. I am going from here to here. Are you getting my point? I am going from here to here. So what is the potential at the center? Potential at the center, that is 3 by 2. Remember, it is 3 by 2 times of R. That is potential at the surface into minus Q. Correct? What is the potential into Q? That is the potential energy. What is kinetic energy? Kinetic energy will be half m Vc square. Now calculate Vc square. Whatever you will get, this will go into that side. 3 by 2. 3 by 2 minus 1, that is 1 by 2. So 1 by 2, that is kq square by how much? Kq square by small q by capital R, and that will be equal to 1 by 2 mvc square. So from here you get Vc is equal to how much? Root over of how much? That is kq small q by m capital R. Clear? I hope it is clear to you. Any doubt till here? Please look at it and tell me. Is there is any doubt? Clear? Shall I proceed further? So let's take one more example. Example number 2. Okay. Okay. I will go a little slow on this session because very important session. So just be patient and try to understand and solve all the questions. Okay. Basically, this radius is R and this distance is R by 2. Okay. Again the same thing. I have charge Q minus Q, mass M, charge Q minus M. Again I'm keeping the charge here. Obviously it will go to the center. Now again my question is same. You have to calculate the velocity at the center. Again the same question. Calculate the velocity at the center. How will you do? How will you calculate the velocity at the center? I hope my question is clear. Again you have to calculate the velocity at the center. How will you do? Again same thing, energy conservation is valid. So what you will do? U initial plus K initial is equal to U final plus K final. First you tell me what is the initial potential energy. Again the same thing, K Q by R. What is the final potential energy? 0. What is the final initial kinetic energy? 0. What is the final kinetic energy? That is clear. Okay sir, it will be half m, sir, some Vc square. But the important thing is that what is the final potential energy? Is it center? No. If we know the potential at that point, we can write the simply we can write the potential energy at that point by multiplying by minus q. First, how to calculate the potential at that point? If you remember the formula, there is a direct formula for this. What is the formula? Kq by 2r cube into 3r square. What is r value? R value is r by 2. Okay, that is r square by 4. This will become 12. 12 minus 1, 11. 11 by 8. So k, so you will get the value as k q square. This will be how much? K q square, not q, sorry, not q square. 8 into r into 11. So this is the thing. Now you have to move this to here. You will get Vc square is equal to how much? 11 here. So 11 by 8 means 11 minus 8 is how much? 3 kq by r into small q, correct, by 8, and we have 2 also, so that we will take it here, and then you multiply and divide by m. So this is the thing we will get. This value will become root over of 6, or we can do one thing, it will be 4 3 k capital Q small q by 4 r into m. That is the velocity. Okay, that is our velocity. I hope these two examples are clear to you. Clear? Okay. Okay, so let's take one more example. Again I have to draw. Okay, let's take another example. Okay. Okay, it is in the middle only, but it don't look like a middle. Let me slide change. Drawing is very okay. Yes. Okay. So this is the thing. Now my question is, suppose there is a charge minus q and mass m is there. This is point A, this is point C, this is the point B. You have to find problem point B. You have to find what you have to do. You have to find, suppose here the velocity is v naught. Oh, sorry. V minimum. You have to find V minimum such that it reaches point B. Means you have to calculate the point like V minimum such that it will reach the point B. That is my question. And you have to solve this. First you have to think. Okay, first thing I will give you 1 minute to think and then tell me the answer. I am giving you 1 minute. Just think about what is a V minimum. How to solve this V minimum? How to find this V minimum? What is the approach? See, it is okay that we have to apply the energy conservation. That is okay. We have to apply the energy conservation. That is not a problem. But what is the approach? How to calculate? First, you tell me, for reaching the point B, if this charged particle reach the point C, it will automatically reach the point B. Yes or no? Okay. What you are saying? I'm saying if it reach the point C, if I provide such a velocity that it try to reach the point C, this charge is not minus. What I am saying that if we provide some velocity, due to this velocity this charge reaches the point C. As it reaches the point C, the electric field is there now, so it will apply the force and it will automatically move to point B. So we have to basically, the question should be that what is a V minimum required to bring the particle to point C, because if it will come to point C, automatically the electric field will try to move this particle to point B. That is automatically will happen. So there is a like what we have to do, we have to apply the energy conservation from point A to point C. There is no need to apply the energy conservation from point A to point B. Most of you have applied the energy conservation from point A to point B. No need. We have to apply the energy conservation from point A to point C, because here the electric field in this direction, so force in this direction. So we have to apply some velocity so that it can reaches here. As it reaches here, the electric field in this direction. So force will be also in this direction. So automatically this will reach to point B. There is no need of anything. So if I apply the energy conservation from A to C, what I will write, initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. Correct? What is initial? K cube into small q by r. Correct? What is the initial kinetic energy? The initial kinetic energy is half m v minimum square. Correct? What is my final kinetic energy? 0. What is my final potential energy? That is 3 by 2 k q by r into small q. Now you solve from here, whatever you will get, that is my V minimum. Okay. Now this you can calculate. So what is the value you will get? 1 by 2. 1 by 2 will cancel out, so you will get k capital Q small q by mr. Correct? The same question as first, if you remember. This is the same question as, if you remember, that is the same question. Is it clear? Is it clear or not? Clear? Any doubt is there? If anyone have a doubt, please tell. Any doubt? Let us take one more example, some another example. I hope now for you it is clear, you can solve any question on this. Let me take one more example. This similar type, but this question. Okay. If my diagram is not proper, just don't like try to understand. That's why I am speaking everything, so that if something I am not able to draw properly, you can note it down. Okay. Because I am not a drawing teacher. or let it be. This is the case. This is the question. Suppose this is a question. But now what I am doing, I am keeping a charge minus q here, having a mass m. This center. And if suppose I displace this charge, basically it is keep here in the center between the tunnel. If suppose I displace this charge here, the force will act in this direction. So it will try to move it this direction. So it will be off. Then again it will go here. The again force will be in this direction. So it will start oscillating at this point. Correct or not? Correct or not? Is it okay for you or not? First of all, it will oscillate obviously. So my question is that what is the time period of oscillation? That is my question. Okay, so how will you find the time period of oscillation? Use your common sense. It's very simple. Use your common sense. How to find the time period of oscillation for this? See, suppose I displace a very small distance x. Okay, very small distance x. Radius is same. Radius is r only. Okay, radius is r only. So suppose I displace. So my time period of oscillation, what you write? E is equal to 2 pi into m upon k. That is you have to find now. So what is the force it will act on this? If you displace in this direction, the force will act in this direction. So I can say it will be q into E. What is the electric field? That is k cube x upon r cube into small q. Correct? So this can be write as minus k cube small q by r cube into x. So this is our k only, na? Just put it here, you will get the time period. T is equal to 2 pi root over of m. How much? Remember this k and this k is different. Okay, don't mix it. That is our time period of oscillation. Simple. Okay, see, this time period of oscillation is independent of x. Okay, clear? Any doubt here? See whether you have if you have a doubt, anyone have a doubt, please tell me. Just take a note of it. Completed? Okay. Let's move to the next question. It's similar type only, or I will give it in last. For that we will solve one more example. Then I will give that question. Okay. Okay, let me ask you first one. Suppose this is one sphere. Beside this there is another sphere. Are you getting my point? There are the two. Something like that. That is there is a, like, basically it's like a hollow type. Inside it is hollow, but outside it is filled. Okay, it is basically it is a sphere only. Okay, like that. Are you getting my point? Something like that. So suppose this is given. Okay, and suppose the radius is r1, the radius is r2, and suppose the rho is also given. Correct? My question is, and suppose the charge is q. Correct? And obviously the charge is distributed here because it is not a conductor. You have to find electric field at a distance r from the center. That is my question. At a distance at this point, what is the electric field? How will you solve? Calculate the electric field. Okay. How to solve? Calculate the electric field. Solve it fast. Don't take too much time. It is very easy question. Don't take too much time. Completed? Okay. So what do you have to do simply? First, what we will do, that's why I told you the derivation. What is the approach? Take Gaussian surface. Okay. Then after that, apply integral E dot dA is equal to, what is the formula? That is Q rho 4 pi 3 R. Sorry, I'm doing directly. Let me write. That is Q in by epsilon naught. This is obvious. E into 4 pi R square into cos 0 degree, that is 1. Q in is rho into 4 by 3. Remember, it is capital R cube. Sorry, not capital R cube. Capital RT cube minus R cube. That will be my volume in this region. Are you getting my point? Okay, sorry. That will be not this thing. I want to write this volume, na? So what I have to do, I have to calculate the total volume and subtract this volume. So 4 by 3 pi R1, that is R cube minus R1 cube. Yeah, this will be upon epsilon naught. Correct? This is the thing. Now you divide it. So what is the electric field you got? Okay, that is rho. What is rho value? First you tell me. That is Q upon by R2 cube minus R1 cube. Correct, sir? 4 by 3 pi R cube minus R1 cube divided by epsilon naught. 4 by 3 pi R cube will cancel out, correct? This will cancel out. So what is the value you will get? That is Q into R cube minus R1 cube divided by, and this is 4 pi R square is also, this will be 4 pi epsilon naught into this quantity, that is R2 cube minus R1 cube, and there is a small term, that is R square. So from here I can write it as K cube into R cube minus R1 cube by R2 cube minus R1 cube into R square. This is the electric. So that is why I am telling you to remember the derivation, because this will be useful for you. Okay, because this will be useful for you. So we have seen some example. Let's move to some other more examples. Another example is similar to that time period only. Let us do a small change in that. What is the change I want to do? The change I am thinking to do is, suppose this is the same sphere. As you remember, initially we have cut at somewhere else from the center. Here also I am going to do the same thing. I am going to cut this at some other place, not at the center. Suppose it is like this. Okay. Okay, suppose I cut here, and again the same thing is there, everything is same. Suppose this point is, suppose this point is my center. Okay, this distance is R, as you know. Suppose this point is given as D. Okay, this is my center, charge is there, everything is there. Okay, I'm not going to draw every time, just assume that yeah, everything is given. Again you are keeping a charge here. Okay, same earlier, as like as it is given, minus q mass m here, and you are displacing now. Okay, again you are displacing it left right somewhere, and it will be, obviously it will be in equilibrium because it is a similar condition, only the position is changed and it will oscillate. Okay, so my question is that again you have to calculate the time period of oscillation. That is my question. It is example number how much? That is example number, sorry, this will be the example number 5 now. Example number 5, this will be the example number. So you have to find the time period of the oscillation. Same question, only we have changed the position, only the position is changed of tunnel, the tunnel position is changed, other thing is remain same. Now you have to calculate the time period of oscillation. How will you do? What is the approach? Just try to solve it. Something don't look straight, just treat it as a straight. It is, I am trying my best to draw it straight, but if you are not able to see something as a straight, just assume it is a straight only, because my drawing is not very good. Okay, just assume it like it is a straight only. Okay, yeah. Okay, so now you have to calculate the time period of oscillation. So how to calculate? What is the approach? How we can calculate the time period of oscillation? Now tell me how to calculate the time period of oscillation for here. See, one thing is very clear. If you understand, one thing is very clear. What is that thing? If you understand one thing, the one thing is very clear that what we will do, we will displace. Obviously, we are going to displace it for distance x. Okay, you see the force, if you displace it, the force will act toward the center, obviously, because the electric field will be like this. Force will act like this. This is my force vector. This distance is given as x and this distance d, and suppose this angle is theta. There will be two component will be there. This is f, how much? This angle will be again theta, so f cos theta will be there. Correct or not? F cos theta, this angle is theta. Similarly, here we have another component, that is f sin theta. Now you tell me which is the restoring force. My net, like basically which force is the restoring force? So F naught will be obviously restoring force, because we have to use the restoring force for finding, because see, this force is going to be balanced by this f cos theta is going to be balanced. Which is going to balance this f cos theta? F cos theta is balanced by normal. You understand? See, there is a contact, there is the, this charge particle will be kept here, so there will be contact, so this is going to be balanced by normal. Okay, this is going to be balanced by normal. Okay, which force we will left? F net we got is how much? F sin theta, correct? This we will get only if, and it will be in opposite direction, minus f sin, because displacement and both are in opposite direction. Now you apply the thing. What is F net? Minus k capital Q small q into x upon how much? Not x, not x. What is the electric field there? Is d na, d from center the distance d upon r cube, sorry, upon r cube to sin theta. Now what is d sin theta? Again k cube small q by r cube. This is my d, this is my d cos theta, this will be my d sin theta. Are you getting my point? This is d, this is electric field will be k q by d, d sin theta will be x only. Will be x. Yes, this will be x. So d sin theta is equal to x. So again my k value is same. So if it is k again, I can say what? This will be my k net. If again my time period is same, if you see. Again I am getting the same value, that is kq, q, same value. So I can say that my time period is independent of the position of the tunnel. Wherever you want, you can keep the tunnel. You will always get the same value wherever you want. You can keep the tunnel, you will get the same value. Clear? It doesn't matter where you are keeping the tunnel. Okay, it doesn't matter. This distance is r. Okay, make it clear. Distance I am taking. Okay, so it doesn't matter. Okay, sorry. We have one did some mistake. I think so. Sorry. This should not be D, na. This should be R, na. 1 minute. So we have to take the point at which the electric field. We are writing for that point, so this should be R. Sorry, one mistake. R sin theta will be X. Yeah, now it is correct. So yeah, so we can say from there it doesn't matter wherever you want you can keep the tunnel. If you want to keep the tunnel here also, here also, anywhere, my time period will be again the same value, mr cube divided by kq into small q. It will be always a fixed value. That is what I am trying to say. It doesn't matter where you are keeping the tunnel, always the time period will be fixed. That is what I am trying to say. I hope it is clear to you. It doesn't matter, just take a note of it. Clear? Any doubt is there? If anyone have a doubt, please tell. Clear? Okay. So this is the example number 6 we have taken. Now the example number 7. Okay. I hope this type of questions you have seen in the exams. Like suppose this is my sphere. Okay. There is another sphere is also there. Okay. My another sphere. Correct. And what I am trying to say, suppose this is my center and this radius is 4r. Okay. And suppose this distance is 2r and its radius is r. Correct. And this is my center. Okay. And this is the center of its center. My aim is to find from distance center to 8r. I want 8r. I want to find the electric field here. Now the thing is that this is a cavity. This is a cavity and the charge is present here. It is a cavity, means I put a one small hole there. Then you have to calculate the electric field. This type of question you have solved. What do you have to do basically in this type of question? What do you have to do? What is the approach to solve this? Suppose the rho is given. Rho is there. Okay. How to solve this? What is the approach? Okay. What is the approach? How to solve? It is very easy question. What do you have to simply do in this type of question? Approach is very simple. Approach is very simple approach you have to apply. Solve this type of question. Okay, what you have to do, simply break this into a two spheres. Okay, break this into a two spheres. That is a simple approach. You break this into a one bigger sphere, one smaller sphere. Correct. The bigger sphere, take this as a plus q. With plus rho. Okay, and with negative this is cavity, you take it as minus sign with minus rho. So when you add this, you will get this thing. Correct or not? Now for this, if you will see, just remove this cavity and you analyze for this sphere. The center, from center at distance 8r, from center at distance 8r, I have to calculate the electric field, correct? So what is the formula? The formula is rho. What is the distance? 8r upon 3 epsilon naught. In this case, if you will see, I have to from center 6r, from the center 6r distance, I want to calculate my electric field. So what is the electric field you will get? This will be minus rho, or no need of putting minus. If you do minus rho into what is the distance 6r by 3 epsilon naught. So what is an E net? So E net will be, just add these two. So when you add, what you will get? This is 3 epsilon, that is 2 rho r by 3 epsilon naught, correct? That is the answer. What is the direction will be there? The direction will be in this direction. This is my E net. Clear? That is a simple approach. What you have to do, you have to break into the two cavities, and you have to simply take one plus rho, one minus rho, and then you have to solve separately, and then you have to add. Means you have to break into a two different questions. You have to calculate and then you have to add. You will get the E net. Simple. Similarly for potential also, and similarly for whatever they will ask. They can ask potential also. You have to do the same approach. Same thing you have to do to calculate the potential. Clear? Let's take one more example for your understanding. They ask lot of question on this. Okay, lot of questions, and you have to do the same thing again and again in all questions. Let me take some another question. Okay, suppose the question state the same thing, same data I am taking. Suppose this is my 4r. The distance from the center is again 2r. The radius is r. But in this case, and this is my center, obviously. What I want to calculate, I want to calculate the electric field at this point. And this is a distance from its center is 2r. I want to calculate the electric field. This is my question. And the charge is obviously distributed here, as mentioned here also. And this is a cavity we have. Rho is given. You have to calculate the electric field at this point. How will you solve? How will you solve? How will you solve? How will you calculate the electric field at this point? What is the approach for this? Just think about it little. I am giving you 30 seconds to solve this. How will you calculate? So what is the approach? Again, we have to break it into two spheres, correct? This is one sphere, this is another sphere. What do you have to do for this now? This one is, I think we have done some mistake here. Okay, yeah, we have done the mistake. Sorry. Yeah, you are saying correct. We have done one mistake. Basically, we have applied the formula of inside formula here. Just change the formula. Concept is correct, but we have applied the wrong formula. Thank you for telling. We have applied the wrong formula here. Everything is correct, just formula is wrong. Okay, other things are correct. Approach is correct. See, what is the electric field outside? It is kq by r square. So what is the electric field here? Kq by r square. R is means 8r whole square. But what is the electric field here? Here electric field will be kq dash. Means the charge will not be q here, na? By what is 6r square. And obviously here the electric field will be in this direction, for this in this direction. So what is E net? E net will be, that is kq kr square to q by 34 minus q dash by 36. Now what is, how to find the q dash? Q dash will be C, capital Q by 4 by 3. What is the radius? What is the radius? 4 by 3. What is the radius for this bigger? That is 4r. So radius for this is, how will you write? C, 4 by 3 to 4r cube into what is the, that is, this is 4 by 3 pi What is the radius for this? That is r cube. So from here, if you calculate, my q dash will be how much? That is q by 4 for 16, 64. So q by 64 it is. Okay, the radius is 4r, radius is r, so it is this much. How we will get? Now you put this q dash value here, you will calculate, you will get the E net in this direction, correct? Okay, so similarly here also, if you will do, it will be my plus q. I am not writing completely. Obviously this will be plus q and this will be plus rho. Similarly we have minus here like that, and it will be minus rho, correct? And then if you calculate the electric field at this point from center to r, what is the value you will get? It will get rho 2r by 3 epsilon naught. This is my electric field E1. Okay, what is the direction here? Similarly, in this case, if you see what is the distance from the center, see, it will be outside point. If you will see, this is 2r, this is 2r, so 4r. So the distance from its center will be 4r, and it will be outside point. So for this, the electric field will be how much? K q. Now we have to find q dash upon, that is 4r square. Now how to find q dash? I told you the q dash will be again, that is q by how much? 64. Now you put it here, you will get how much? K q dash, and this will be in which direction? See, if you keep, it will be in this direction. That is my E2. My E2 is coming. So what is my E net? This is my E2. So what is my E net? You will get, my E net will be how much? That is E1 minus E2 vector. Sorry, not E1 plus E2 vector. So just subtract these two because the direction is opposite. So k q dash k, that is rho 2r by 3 epsilon naught minus, what is the value here? It will be k q dash upon 4r whole square, and whatever the net value you will get from there, you can decide the answer. Basically this value will be, just you have to put the value of rho here. Q dash, you know what is the value of rho? Rho value is simple, it is q upon 4 by 3 pi into 4r whole square, sorry 4 cube. Just put this value here and do the calculation, you will get the E net. If it will come positive, then in this direction. If it will come negative, then in this direction. Clear? So this is our example number how much? 8. Clear? So in this session, we have seen basically all the formulas, applications, whatever we have learned in the last session. So this is how we completed our basically the conductor part. Okay, and that is a very large portion in our electrostatics, and we have completed that part. Now you can practice any question from any book or anywhere. Now in the next session, we are going to discuss about the next things. Next few things are left there. We will discuss those few things, and then we will proceed to the next topic, that is our next chapter basically, that is current and electricity, and then we will move to the capacitor, because after current and electricity it is easier to understand the capacitance, then we will move to the capacitor. Okay, so till then, best of luck, do your preparation properly, and if you enjoy the session, like it, share it, subscribe it, and have a nice day. Thank you.